Hello, my name is Mohammed Idris, and I would like to present my research paper, which is titled Machine Learning and Deep Learning for Urban Mobility: Predicting Bike Rentals in a Metropolitan City. The abstract provides a concise overview of the study, outlining its objective, methodology, key findings, and conclusions. Now I will proceed to present each of component in greater detail. The concept of public bike-sharing systems has emerged as a promising solution, providing an eco-friendly alternative to traditional mobility. The concept behind the idea revolves around providing bicycles for shared use on a rental basis for short-term trips. The benefits of bike-sharing systems include providing a cost-effective way to travel that minimizes users' personal carbon footprint, addresses traffic congestion, enhances overall traffic flow, and promotes public health. Capital Bike Share is the largest bike-sharing system in the United States, currently operating over 7,000 bikes across 788 stations in a Washington metropolitan area. This study addresses two key problems. First, Motivate International, the system operator, faces the ongoing challenge of meeting the rising demand for bikes. A significant 31.3% increase in trips in 2024 compared to 2023 has amplified operational pressures, requiring frequent maintenance and repairs, timely bike rebalancing, and the capacity to handle higher demand during peak hours. Second, the worldwide uh, demand for dockless bikes reached a 60% market share in 2023, up from 45% in 2020, which requires an investigation within the capital bike share system data for further decision making. This research addresses two gaps in the literature. First, the generalizability of previous studies is limited because of varying urban infrastructure, weather conditions, population densities, and commuting behaviors across different regions. Second, existing studies have treated bike demand prediction as a black box modeling task, and limited efforts have been made toward model explainability. Therefore, this study aims to utilize machine learning and deep learning techniques to predict the hourly bike demand for the capital bike share system in the Washington metropolitan area. More specifically, the study aims to build ML and DL models to predict bike rentals, to compare and select the optimal model for predicting bike demand, to identify the most important features contributing to bike rental predictions, to provide recommendations to the capital bike share system authorities for enhancing the bike sharing process. In the literature, ML algorithms have been applied to predict demand in various industries and sectors, including retail, automotive, energy, aviation, and tourism. Two important themes found in the literature. First, studies in all industries, including the bike sharing industry, show that tree based ensemble models such as random forest and XGBoost consistently outperform baseline models like SVR, DT, and KNN. Second, DL and hybrid DL models further outperform traditional ML models, especially in time series and complex sequential data. This study followed a structured six-stage methodology to ensure comprehensive and systematic analysis. It began with phase 1 initial data preprocessing, focusing on data cleaning, feature engineering, and data wrangling and transformation. During this stage, the dataset for this study was created by merging two datasets and engineering important features. Phase 2 Data Exploration. It involved understanding data distributions and identifying patterns in the data. The third stage was Phase 2 Data Preprocessing for Modeling, where the dataset was made ready for model training. In the model building stage, seven models were developed. This was followed by model evaluation, where models were assessed using three performance metrics, which are R squared, mean absolute error, and root mean squared error. Finally, sharp analysis was conducted to interpret model predictions and identify key contributing features for prediction. The final dataset for this study was obtained after phase 1 of pre-processing by merging the trip dataset and weather dataset that were obtained from Kaggle website, and then engineering temporal features during the process. The final dataset included 19,006 records with 21 features. There were two data frames created for training: DF1 for ensemble methods and DF2 for linear regression and DL models. The dataset was then split with a ratio of 80-20 for both DF1 and DF2. An additional 90-10 split of DF2 was done to check the DL models improvement with more data. The model strengths in this study were 5 ML algorithms, which are linear regression, decision tree, random forest, gradient boosting machine, and extreme gradient boosting tree, and two DL algorithms, long short-term memory and gated recurrent unit. Summary statistics showed that the average number of bikes rented per hour varies significantly. Additionally, electric bikes are rented more frequently than docked bikes, but classic bikes still dominate demand. Time series analysis revealed that there was a consistent year-over-year increase in bike rentals, with peaks during summer and dips during winter seasons. In addition, the demand for electric bikes shows an increasing cyclical trend over time. The model evaluation results revealed that linear regression had the weakest predictive performance accuracy among all models. Moreover, decision tree and DL models such as GRU and LSTM showed comparable results, with DL models achieving higher R scores but also higher MAE and RMSE values. In contrast, tree-based ensemble models such as RF, GBM, and XGB3 significantly outperformed all other models, achieving the best performance across all evaluation metrics. These discussion points highlight the major findings from the study. First, tree-based ML models, particularly ensemble methods such as RF, GBM, and XGB3, consistently outperformed both the linear regression and DL models. Their higher accuracy is attributed to their ability to model nonlinear relationships and complex feature interactions effectively. Second, DL models showed improved performance when trained with a 90-10 split compared to 80-20, highlighting their need for larger datasets to outperform ML models. It should be noted that DL models demonstrated stable performance in the study and showed the lowest degree of overfitting compared to ML models. Overall, it was found that extreme gradient boosting trees was the champion model for predicting bike-sharing demand, with an R-squared of 97%, an MAE of 43.70, and an RMSE of 75.38. Also, sharp analysis showed that 9 features contributed the most to the champion model's output, as shown in the figure, with the hour feature being the most important for predictions. The first recommendation for the system operator is to ensure peak hour readiness by reallocating bikes to high demand stations and areas and ensuring maintenance during low usage hours. The second recommendation for the system operator is to gradually expand the electric bike fleet to meet the growing demand. For policymakers and urban planners, demand dips in winter periods suggest the need for investing in weather-resistant bike lanes and safe winter infrastructure. This will help sustain year-round ridership. For future research, it is recommended to improve on the limitations of this study by incorporating station-level data, applying different feature selection methods, exploring different encoding methods, and exploring an automated hyperparameter tuning techniques. In conclusion, the study achieved all its objectives. The first objective, which involved building ML and DL models to predict bike rentals was successfully achieved. Seven models were developed: five ML models and two DL models. The second objective was also accomplished, which focused on comparing these models to identify the most accurate predictor of bike demand. The XGB3 model was found to be the best model for prediction. The third objective, which involved identifying the most important features contributing to bike rental predictions using model explainability techniques, was also achieved by performing sharp analysis. The final objective, which is to provide recommendations for enhancing the bike sharing process, was also achieved. Recommendations were provided for the system operator, policymakers, urban planners, and future researchers. Thank you for listening.